Hello again. This is DI504, Foundations of Deep Learning, and this is the second week and second lecture we are going to do together. In this week, I'm going to be talking about fundamentals of machine learning because this is an introductory level deep learning course. And in order to be able to properly understand the fundamentals of deep learning and foundations of deep learning, as the name course title implies, I think you need a little bit of knowledge about the fundamentals of machine learning. And in this course, we don't have a prerequisite condition. So most of you did not have any introductory level machine learning course. However, if you did, the things that I'm going to be talking about to you today may sound trivial, but it's okay. We'll visit some concepts together and try to understand what fundamentals of machine learning is. And before that, what does it mean to be a feature in machine learning? Because that's the main subject today, because this will lead us to more high level and abstract features that the deep learning architectures will create for us. Good. So I continue. Let me continue. Okay, so we're going to talk about the so-called feature spaces, how features are represented in spaces. And we'll continue with some machine learning fundamentals. To understand what a feature is, I think it's always best to start with that toy example, which we can visualize. When I say visualize, I mean to visualize the dimensions of a feature. A feature is something that represents data. I mean, the data is in itself is a raw thing. I mean, in a raw data, we have all the numbers or values or the structured information, whatever. However, if you have features, you had some sort of processing to extract knowledge from that data. And feature extraction is a very important step. And as I mentioned the previous week, feature engineering, pattern recognition, was the main title of artificial intelligence about a decade ago when I was doing a PhD. Those handcrafted feature engineering days are over. I mean, not exactly over. In many fields, we are still doing that because it is beneficial for edge devices or some applications. We don't have enough data to apply deep learning. So feature engineering still exists. But deep learning broadly manipulated the field, and we are not doing feature engineering as we used to do before. So what was that feature engineering? To represent data at a higher level with a representation, with a mathematical representation. And when I say mathematical representation, I'm talking about some vectors. I'm representing something, a concept. It could be a person on a social media, the profile of a person on social media, or it could be an image. Doesn't matter. I'm representing it with numbers. And when I'm representing with something with numbers, I'm using vectors, matrices, or tensors, high-level matrices. In that case, I will be talking about dimensions. So each value of that, each value of that vector will mean a dimension to me. Okay. So let's talk about dimensions. So I'm going to be doing a toy example in which I'm going to be analyzing apples and pears. Well, that's the proper example that we toy with children. Is this an apple or a pear? And I'm going to try to define apples and pears mathematically using vectors. Although it sounds trivial, it's going to give us true insights about what machine learning is trying to do with this feature engineering. So I'm going to define apples and pears according to their color and shape. You can define anything with multiple abstract concepts. These are the ones I have chosen. So as a matter of fact, when I define apples and pears by their color and shape, I'm defining a feature representation for them. And I'm limiting my representation to these two concepts. That's why the feature space I'm going to create will be two-dimensional. One dimension being the shape, the other dimension will be color. And for them to be dimensions, vectored values, I'm going to quantize those values. So because color is something that you can express by words, it's reddish or it's bluish. I'm going to be mapping those words to values, okay? And I'm going to map, since this is my space, apples and pears, I'm going to be mapping the color space between red and green to a number value, because we don't have blue apples in the world. I mean, we might have, but I'm not going to cover them. It doesn't matter for me. I mean, if there are blue apples, my system won't be able to process them. I don't care. This is something you will always do in data informatics. I mean, if something is an outlier that would affect the training of your system, you don't care about those data. And the shape. And I'm going to be defining the shape in a scale of spherical to oval. What does it mean? So I'm using two measures and I'm creating a two-dimensional space. And about the quantization, these are the things that I'm selecting. Actually, what I'm exactly doing here is I'm doing feature engineering. I'm quantizing an abstract feature to numbers. This was the very first feature. I mean, in 80s, people have done this in 70s. But the feature engineering you did in 70s and I mean, in the previous decade, fundamentally doesn't differ. I mean, what you do is you handcraftedly design features and quantize them. That's what we are doing right now. So what I'm going to do is I'm going to define the color dimension from red to green using values from -3 to +3. Why? My choice. I'm going to be quantizing them to these real values. These are the numbers that I use. And about the shape, I'm going to be using from oval to spherical change using -3 to +3. So +3 will perfect spherical. And -3 will be the most oval. I don't know what that's supposed to mean, but I choose maybe in my data set an apple which is oval or a pear that's oval. And I imagine any apple or pear cannot be more oval than that. And I set that value to -3. So I engineered this. This is feature engineering. So this will create a space for me, guys, like this, like a feature space. So in the X dimension, I have this color thing from -3 to +3. And in the Y dimension, I have the shape features from -3 to +3. And I can get two samples, one apple, one pear. I look at them, I'm the sensor, I decide. As a person, this is not a fully automatic machine. I'm just calculating those values. Or if you had some sensors, I don't know, maybe you have designed a sensor which looks at the apple and extracts that value. I mean, its shape value is 2.7. It could be the case, or you could be defining, because what we're doing here is to theoretically define the feature space. So this apple is something like shape. When you look at its shape, it's not a perfect sphere. So I imagine it is 1. These are some values, don't care about. It could be 2 as well. Doesn't matter how perfect the values are. And about its being red, it's closer to, it is not correct, guys, because this should have been red, this should have been green, right? Yes, because the color scale is reddish towards this side, the color scale is greenish towards this side. So guys, let me correct it in the video so that you know that it's corrected. This is plus. And this is minus, okay? Okay. So what I do is, I put these samples. What I'm trying to do is, basically, I'm trying to differentiate apples from pears. Can you find a mathematical function to do this? If you had only these two samples, it would have been very easy. Yes, you could just put a line in between, which is f of x equals y. That will separate it for you. But if it was the case where you only had this apple and this pear in the world, in your training set, or specifically speaking, that's not the case. So what happens in real world is you have more reddish pears and you have more greenish apples. In that case, you collect more data. That's another thing that you do in feature engineering. But when you collect new data, you realize that in the feature space you've created, a linear model, which was a line in a two-dimensional space, a linear model in a two-dimensional space is a line. And from calculus, you know that a linear model in a multi-dimensional space is called a hyperline out of n dimensions. I would have to use a more complex decision surface. In machine learning, this guy is called a decision surface. It decides for you, but it decides that decision for a specific purpose you define, which is the problem definition. our problem definition in this case is apples versus pears when I'm trying to classify, a binary classification problem. If I have defined the problem in a different manner, it would have been different, but I'm focusing on that problem. I'm trying to build up a feature engineering example for that case. So what I do is, I try to find another decision surface. I still can find a line. In machine learning, if you can find a line to separate your surfaces, that's good, guys. Linear discriminative functions are usually the most robust ones. That's why methods like support vector machines try to warp the feature space to a shape where it can find a linear classifier in it. If you have never taken a course about support vector machines, I'm trying to give you an idea about it. I was just talking about a concept which is called the kernel trick. You don't have to know, it's beyond the scope of this course. But in this week is about just making an introduction to machine learning concepts. That's what I'm trying to do. I still could find a linear surface. That's why I did this. However, if you collect more data, you'll realize that there's something which doesn't look like an apple or a pear. I know that it's a pear. I mean, you also know that it's a pear because you're perfect beings. So what I'm going to do, in this case, it looks like in this two-dimensional space, there is no way I can find a linear discriminative surface. And actually, most of the problems we model cannot be solved by linear discriminative functions, guys. Simple problems can be. So problems that are not related to deep learning, more simple problems, expert systems or intelligent systems, they still use these kind of linear discriminative surfaces because they have simple problem definitions and simple feature spaces. So I strongly recommend you take a machine learning course as well. In our department, we have one. Not in our department, when I say in our department, it is MMI. In MMI, we have 702. I strongly recommend. However, in real world and in deep learning, it is not the case. It is usually a non-linear discriminative surface. That's why linear classifiers will not work. This is very important, guys. Linear classifiers not working will lead us to an important result where in neural networks, we will have something called an activation function, which has to be nonlinear. This was a long jump, which you were not ready for, but I'm trying to incept ideas to your head. That's why. I had this function, but I still have problems because I will have a pair like this. In that case, I will need more complex functions. But as you make the function more complex, as you make the decision function more complex, you will start to do a phenomenon called overfitting. You will be fitting to your training set too much. It will be like avoiding the things in your training set and creating a decision surface which would perfectly fit your training set. However, when new data comes from outer space, maybe it won't give you the accuracy that you need because of the outliers in the training set. So in machine learning, there is such a concept like, okay, you use the training set to find those decision surfaces. However, you have to make a balance between the generalization and the outliers in your training set, which is called overfitting. If you cannot make that balance, that trade-off properly, that's called overfitting. A new concept, guys. If you have never heard about overfitting, it will be a concept we will be, talking about a lot in this course. Overfitting, another fundamental machine learning course. So what I can do is, whatever you do when you overfit, there will be new outliers to overfit. So overfitting more is not the solution. What you have to do is, you have to generalize. And to be able to generalize, what you need is a large data set, and in that data set, balanced information, a proper representation of the actual system, of the problem you have. If you have a data set in which you have these strange pears and apples, you won't be able to train your system because that's not the real world. It won't make sense. Most of the time, when you're building up an automatic system, it's okay when you do once in a while some mistakes. It doesn't make sense for a human being. I know a human being won't make any mistakes, but believe me, even human beings make mistakes. So when you're designing a mathematical machine learning model, well, you just have to construct a training set where the outliers and the generalization is balanced. This was a representation of that balanced data set, that discriminative functions, linear classifiers, and overfitting. The dimensions that we're going to use in our world, especially in deep learning, will be hundreds of thousands of dimensions because it will be the dimensions of the weights we use. So it is impossible to visualize them like this. That's why we start with a 2D visualization, which will make sense for us. It's difficult to visualize a hyperplane. I mean, a hyperplane in 8 dimensions is something you cannot visualize, but you can mathematically comprehend. Good. So it will be wrong classification if I use this, but it's okay. Outliers being wrong classified is something okay. Okay, let me delete that drawing I've done. Okay, so at some point you may conclude that the features you use to decide whether it's an apple or pear is not enough. So that's another point. Okay, whatever I do, the overfitting continues, and I think it is not working. In feature engineering, what you do when you have that feeling is you come to the conclusion that the feature space I've selected is not working. It's not working. So maybe I should have engineered a better feature space in machine learning, we say. However, the funny thing about this course is, which is Foundations in Deep Learning is all about not engineering that feature space, constructing models which will construct the feature space for us looking at the data. That is the revolution. That was something that I mentioned previous week. So deep learning revolution is all about the models deciding which features to use, looking at the data, automatically using an optimization function. That's it. That's a very brief summary of what happened in 2012. Okay? And this is called the feature space. Enough or not, you use in feature engineering, you change, you add new dimensions. Maybe just you add taste. If you have a taste sensor, you can add a taste sensor. And when you add a taste sensor, I mean, it's a bit science fiction, but maybe you have a better classification because pears and apples usually taste different. So a decision is a separation, which is a line, surface, or hypersurface in an n-dimensional feature space. The very fundamental concepts of machine learning. So let's look at the real data. A real data in this space would look something like this. Colors, right? And you can see there are a lot of overlapping in the samples, which makes us think that, well, it is difficult, and whatever I choose, there will be wrong decisions. This is the capacity of this feature space. If you had a third dimension, for example, if you had a third dimension here, like this, the Z dimension, where, for example, the red ones will move deeper than in a three-dimensional plane, I would be easily separating them. So that feature engineering was not enough for me. Actually, that is called the kernel trick, and that's the beauty of support vector machines, which is not the scope of this course. Okay, so that's what we could do in our 2D space. Somebody, thanks to them, collected color and shape values for these apples and pears and have constructed this space, and it looks like this. So what we usually do in these cases is, if this is the feature space we have, we construct a linear classifier and live with the wrong decisions and live with accuracy. Why I told you this is because in today's real world machine learning systems, this is usually the case. That's why usually the machine learning systems of today, non-deep learning systems, because the world is quickly changing to a deep learning applications. But before that, like 5 years ago or 10 years ago, most of them did this. And that's why they didn't work well. That was the reason. That was the mathematical depiction of why things didn't work with machine learning. Apples and pears, but you have apples here, you have pears here, and there are many errors. So for example, like this, a reddish, less oval pear, which you eat and you decide to be pear, but looks like an apple. So our decisions were wrong because our features were inadequate. Because when you engineer features handcraftedly, they will always be inadequate. That's what we learned from deep learning. Because our discriminative surface is inadequate. whatever surface you can create in that feature space will be inadequate because of the inadequacy of the feature space. But as humans, we never make mistakes. I mean, we do make mistakes, but we don't make these much mistakes. If you give me a red ovalish pear, I would eat it and say, that's pear. Why? Because of two abilities. I have fantastic senses, and I have more quality features, not low-level features like this, colors or shape. I have, this feature space has the concept of color being reddish or greenish. But in my head, I have the concept of being appleish or pearish, which I cannot explain to you, but when I say you understand. I mean, if you ask me what is like to eat an apple, well, I will have to write a song or I don't know, a poem for you because it's so complex. But we have these features, and it is our ability to construct and share these features that makes us very intelligent beings. So maybe the effort in artificial intelligence should be to achieve those features, guys. And that's exactly what we do in deep learning. We use these complex features, which we also call as the abstract features. We, as humans, actually, psychologists, cognitive scientists, define this as schemas in our head. Schemas for every concept. And a schema is not like a regular feature. We organize our thoughts with relation with other concepts, which would construct them to a very high level representation, which cognitive scientists choose to call a schema. You have a schema of an apple in your head. When I say apple, the understanding of apple goes to very deep meanings from, I don't know, Alan Turing to this Macintosh devices and to the things you eat. It's a combined knowledge, big feature. That's why you can define abstract apples and pears. For example, that machine would never solve this. But when you see these statues, you immediately say an apple and a pear. We have no problems with this. Because the schema and the usage of abstract features you have is highly complex. How can we achieve this? There are two ways to achieve this. One, you need lots of data, which will require these. Because without these being in your training set, even you as human beings will have difficulty to relate those. If you try to understand that relation, think of children, like a 2-year-old or 3-year-old. The first time they see, I have got a 7 or 3-year-old, the first time they see a statue like this, they are overwhelmed because that abstract feature grows a bit in their head. Daddy, it's an apple, but it's stone kind of. So they make that connection. They make that abstract feature more complex and complex. They grow that schema. That's what we have to do. We have to be able to construct models which would be able to get any kind of data and would have the capacity to make that relations. Because what this statue, what is it that this makes this statue look like an apple is maybe the counters, maybe the shape, very slight of features we could relate. Now, that's the ability we should get. And this is a very sophisticated ability, guys. This ability of human beings is the ability that gives us to make very sophisticated things like art and understand. Please. Yes. Yes, that's what we are trying to do. So you're asking. Yes. This is the fundamentals of machine learning part. So it's okay. Okay then. Okay. So you remember this picture from the previous week? And when we get to those schemas in our head, just like I told you, we have very strong schemas about this photo. I mean, some of you might even think that the girl is the daughter of the women because of the familiar features in their faces. We extract this deep level data. What we need to do is to construct those features first to be able to do deep learning. So, okay, this was the relation of machine learning to deep learning. And before the deep learning revolution in 2000, beginning of the decade, the previous decade, 2010s. In 2010s, early 2010s, we had this. What people called this problem was the semantic gap. We could apply feature extraction to images or other signals, but in the end, we had a large semantic gap we couldn't just go over. And the semantic gap was overcome by constructing high-level features using deep learning architectures. Good. Okay, what kind of features can we obtain? Well, that was, as I told you, the main problem of feature engineering and pattern recognition in 2000s. I had my PhD in the last part, in the second part of 2000 and between starting from 2005 to 2010, and the artificial intelligence field was crazy about it. CVPR workshops, CVPR papers were all about designing handcrafted features and applying different machine learning methods to them. And in the last 30 or 40 years, the scientific society came up with many different features, from edges, corners, starting from 40 years ago, to high-level complex features, histograms, gradients, or histogram of gradients, scale space features, transform invariant features. Transform invariant means when you rotate the picture, the value of the descriptor or the feature does not change. So they were working on this. And we still use them, actually. We use them compared to deep learning features because they are cheaper to calculate. And in some devices, if you can solve it, you still use those because of, I don't know, power requirements or computation requirements. So that's still a field. Or in sound, we have the FFT coefficients, fast Fourier transform, or spectrograms, capstone coefficients, mel frequency, MFCC, if you're working on sound processing. If you're from MMI, you just taken Hussein's course, you know these, all of these, and more. How to define more features. So this is like the history of it. This is before 20s, traditional pattern recognition. You have a signal. You design a feature extractor. You transform the signal to the feature space, which is most probably transform invariant and more robust. So you get the necessary information from the image, and it's transform invariant, which means when you apply a transform to this image, your features are robust, they don't change. What can be a transformation? Rotation could be a transformation because the guy who's taking the picture may rotate it. If you're still trying to detect a, I don't know, yellow car, it should be robust to that change. Or affine transformations. Affine transformation is like shearing the image, which is something similar to perspective transformation, right? Because you're taking the image from here. If you're taking the image from another angle, if you're at some distance from the target, it would look like an affine transformation in the target. So if your transform feature extractor is invariant to affine transforms, you won't be affected, so that you will have a more robust system. And when you transform those images to a higher level features, you just fed it to a classifier. Classifier is a decision system. It could be a linear classifier in which you look at the value of the hyperplane. It is on this side of the hyperplane or not. Hyper decision surface on this side of the surface or not. Or it could be some other technique like support vector machines or some generative techniques, Gaussian mixture models, whatever. It was a trainable classifier. And in a machine learning course, you get an idea of these classifiers and different machine learning techniques. But the systems engineering model was this, nothing else. Signal, handcrafted features, feature space representation, and the trainable classifier you train to get an answer to your problem definition, classification, regression, whatever. And the feature extractor changed according to the signal type. For images, we had a list of features. For sound, we had another list of features. For text, we had another list of features. For example, spam. Spam filters are, you have been using spam filters for more than 20 years now. And 20 years ago, it was bag of words, actually, bag of words algorithm, which is a famous machine learning algorithm again. It was first used and first generalized for spam filters because it was giving very good results. Good. In time, the features, handcrafted features, evolved. People have come up with the idea that using very simple features like edges did not work. We have to construct very sophisticated features. For example, the famous SIFT, if you are doing computer vision, SIFT, scale invariant feature transform, was one of those mid-level features. When you're using these mid-level features, which are, by the way, unsupervised, which means you don't get their parameters from a set of a training set. You design them. How you design them? For example, I'm going to talk about SIFT. You have an image. You take different scales of the image by applying Gaussian operators. And you get the difference of Gaussians between the scales. You get the difference. And you try to extract blobs, which are called the scale space blobs, which are defined as features. And you define descriptors around them. I'm just trying to summarize it, but it's a very sophisticated process. I recommend you read the paper. It's by Lowe in 2004. This was a very sophisticated features, and decided that if we use sophisticated mid-level features, still handcrafted, still unsupervised, well, we get better results. And the society was running that way until they hit the deep learning. So this is, for example, histogram of gradients. SIFT was another example. Histogram of gradients was another example. In histogram of gradients, you just, this is a mid-level sophisticated feature, handcrafted as well. It's an example from vision. You just grid the image to some parts, and at every single grid, you calculate the gradients. What is the gradients of an image? Gradients of an image is, consider this part, these gray values, as depth values. I mean, imagine that these white parts are higher ground and black parts are lower ground. And the direction of the, if you just, so that makes like a map. So that's a height map, right? The gradient is where the ball will flow when you just drop it. Those gradients, so this part will have different gradients. In a pixel, you have a gradient to this direction. In a pixel, you have a gradient to this direction. You get the distribution of these gradients. You have a histogram of gradients. And you just calculate the histogram of gradients for each part, and you represent the image as a histogram of gradients. Well, they've come up to the conclusion, this is from 2006, Dalal, I guess. And experience shows us that in pedestrian detection, histogram of gradients worked very well. That was how machine learning society worked those days. Good. And after 2010, people started to work on high-level features, which are still supervised. But as the features got higher and higher levels, things didn't work well. Because apparently, we human beings, who are the guys who are designing these high-level features, we are engineering these features, right? So it was us who designed these features, edges, it was simple. It was us who designed these features. But when we tried to design higher and higher level features, we've realized that, okay, we can understand concepts, but we don't actually understand how we understand concepts. We don't have an idea about how we understand. If I ask you, you see somebody on the street that you haven't seen for 10 years, and you recognize them. Tell me how you recognize them. You won't be able to. It's a vague feeling. Oh, I know something in your face, but you cannot tell. If you're not a great artist, that's an artistic skill, you cannot, because the features you construct are not transparent. Those are not something you've decided. It is not like, do I know him? Let me check this feature. I know. It was not like that. So apparently the type of intelligence that we are trying to reach in machine learning, which we want it to be like us, wouldn't be that way as well. We need a machine that would automatically extract those features, which will not be transparent. Or if we can analyze them. We are going to do this. We're going to do analysis on deep features, but not yet. First, to obtain them, we need maybe a non-transparent mechanism like human beings. Beauty of deep learning. So, right. So with deep learning and convolutional neural networks, age of handcrafted features ended. Now, deep learning learns features are deep learning learned features, learns which features are necessary and uses them for that purpose. So all features are learned, all guys, low, mid, and we are going to visualize them at the early and initial layers and the deep layers of a deep learning. How? That's the purpose of this course. I'm going to get there, of course. So, I'm going to talk about intelligent decision and good features a bit more to give you an idea about these important concepts of machine learning, because that's those concepts we need. We need them to understand the following concepts of deep learning. Deep learning is constructed on top of this. So it is not like when deep learning came, all the previous information became obsolete. No, it is built on that information mountain of pattern recognition, feature engineering, and deep machine learning. Okay, a feature may serve a concept, intelligent decision. When I say concept, actually it's an intelligent decision you make. Whereas it may not for another one. Remember, features are correlated with the decisions you do. And if you want to recognize a person, maybe their facial features may be important. But if you're trying to make another decision about them, I mean, how many friends they have in Facebook, most probably it's not related to the feature, facial features. It may be, I mean, it may have a low correlation, but it's about their social skills, right? So a feature may not always relate to a decision. That's why the features engineered by deep learning or whatever, should be engineered or learned according to a problem type. And that's the beauty of it, guys. In deep learning, and actually in humans as well, if you can make good decisions, because you're using features which were trained for that decision. And if you you didn't have to do any decision in your life. When I say decision, I'm talking about a skill. For example, basketball playing. You don't have the necessary features in your head to relate to the ball and just the rim and whatever. So you learn the features from the data. That's why the handcrafted feature age, which was an unsupervised learn of constructing the features, designing the features, ends with deep learning as well. In deep learning, the features are also data-based, which is the training-based, which is large-scale data-based. So guys, this is a graphical example of why features would be useful for a purpose. So if you have a purpose and the purpose is designated by the colors, what I'm trying to do is I'm trying to discriminate blues and reds. So in ideally, you want them to be separated like this. But this is usually the case. However, if this is the case, maybe you are not using the necessary features. That's how you decide. That's why in data analytics, we usually do something called data visualization. And in data visualization, we try to visualize features in some visualizable spaces, because data is most usually n-dimensional and you cannot visualize n dimensions. And you look for this. Are my features properly discriminating the decision I'm trying to make? Whatever deep learning based features or not. So don't think that this is something related to machine learning or feature engineering. You are going to construct deep learning systems and you're going to come to a point, well, my deep learning model doesn't work. I don't know why, you're going to say. The first thing you will do is you are going to cut your network at some point, get some deep features from a set of data for blues and reds. You're going to visualize them and say, wow, my deep learning system cannot create the features that can be discriminated in that space, you would say. So it doesn't matter if features are engineered or deep. This is the thing that you're looking for when you're trying to build a learned system. Okay, any questions, guys? I don't hear any voice from Zoom, so I hope you're hearing me. If you have any questions, please do not hesitate to interrupt me, okay? Okay, so this is like, yes, ideal and realistic. I have problems. You see, there are outliers. It's not going to work. Nothing works. Even Google's platforms doesn't work 100%, or Amazon's. I mean, hundreds of engineers working there, but it's never going to happen because there's something called outliers in data informatics. You know what it is. And this is poor. If this is the case, don't bother. Find new features, learn new features, try new methods to train new features. That will be the strategy. So when we say features, we came to another definition, which is called the distance. Distance is also a very important concept in machine learning. We're not going to delve into it deeply in this course, but I think that's something you need to know. When you create a feature space, you inherently create the concept of a distance between samples. And that distance is related to the feature space dimensions and your measure of distance. You don't have to necessarily always use an Euclidean distance with features, because in this space, well, the Euclidean distance between these guys is, let me just draw it so that I will use my pen. These two guys is calculated like this. I cannot do it, sorry. So this is the so-called L2 norm, Euclidean distance. That's not necessarily the case. I mean, there are a lot of distances. L1 norm, Manhattan distance, normalized, standard deviation normalized, L2 norm, and it is called Hellanobis distance. There are different types of distances. And in machine learning society, they have realized that we could further manipulate the feature space by creating more complex distances. And they've used distances as well. And frankly, in deep learning, we won't deal with it either. The distance and the features will be inherently and automatically learned by the deep learning system. Because the thing about distance is, it doesn't necessarily have to be regular. When I say a regular distance, what I meant, let me get there. So this is Euclidean distance, Manhattan distance, Hellanobis distance, and whatever. So this is the covariance matrix, which the inverse of the covariance matrix, which means you are normalizing a distance dimension with its variance and its covariance with the other dimensions, which means if a dimension of the network, one of your sensors, is highly noisy, you don't take it into much account, kind of. This might be useful for kind of distance when you're doing machine learning. But these are all automatically learned in deep learning. So when I use the word regular distance. As humans, when we say distance, we automatically mean Euclidean distance. That's how we perceive the world, because a great part of our brain works for perspective projection, and we are very good at perceiving the 3D world so that we make our muscles move and etc. However, the distance does not necessarily have to be regular, which means obeying the triangle rule. And actually, most of the deep learning systems or data analytics problems, you will come up with problems where you will have distances which are not regular. For example, I have an example, right? Yes, what was the triangular inequality? So it is like you have a distance, there are 3 samples, and the distances are according to the triangular inequality. So if I'm closer to somebody and I'm closer to the other person, the distance in those 2 people have to obey a rule. Shouldn't be more than sum of my distances, and should not be less than the difference of my distances. This is triangular inequality, you know this. But this is not necessarily the case, because you will have some sort of data which does not obey triangle inequality. I have an example. Yes, the bodiness measure I defined for social media. People, I mean, I have somebody I like, somebody I don't like. I like it again, but they don't like each other. This is not triangular inequality. So you will have to learn these features as well. And now you don't have a triangular inequality and regular distances. Actually, it is where most machine learning systems start to have problems. It is difficult to make them converge. So in those cases, they use different features. They carry the information to a different feature space, which is more like a regular distance space, and use their optimizations, or they do the so-called distance learning problem. Distance learning is not learning the feature space, but learning the mutual distances between the samples. Distance learning, again, an important title of machine learning, which we're not going to cover, but I would like to mention as a part of fundamentals of machine learning. Okay, so within abstract semantic feature spaces, intelligent systems like AI or you guys usually define distances that do not follow triangle inequality. Consequently, most of the time, the hypersurfaces we define are not linear. So when you don't have a triangle inequality in your space, the type of decision surfaces you construct becomes more complex. That's why we need models that can create very complex surfaces. But on the other hand, we have the problem of, remember, overfitting. In deep learning, our biggest problem will be not to overfit. So deep learning is like, it can manipulate large data, create very complex surfaces, unlike previous machine learning methods, but we have the problem of overfitting. That's why we need very large scales of data. The main differences of deep learning compared to machine learning. Okay, I got 2 minutes. So the trademark of deep learning is to handle this non-linear relationship because they create abstract features. They create non-linear relations between these abstract features. I'm going to talk about a famous clustering method in machine learning, which will give you another idea about, which will give you further idea about these feature spaces. But in the next video, do you have any questions before I stop the record? And Zoom, do you have any questions? Okay.